Today is Wednesday, March the 15th. This is Mr. Hobbs A.P. Chemistry class, Main Park High School. Today we're going to be talking about pH of polyprotic acids. So the first question I have to ask you, what is a polyprotic acid?
Many proteins. That's unique.
Okay? So if I have our most common polyprotic acid, carbonic acid, when it goes to ionize, how many hydrogens does it lose? One at a time. So we're going to get H plus HCO3 minus. And if you look at the chart back there, it says Ka1 for carbonic acid, H2CO3, is going to be 4.3 times 10 to the minus 7. But then we go to lose the second HCO3 minus. We're going to lose the second hydrogen, H plus CO3, 2 minus. Now, what do we expect the value of Ka to be for this second one? A lot bigger? Meaning it's going to ionize to a greater extent? A bigger negative number is what I think you're meaning. So it's going to be a more negative value. So Ka2 is going to equal, and you go up there and you look, it's 5.6 times 10 to the minus 11. Okay? A factor of 10,000 times smaller value of Ka. So when we go and look at, we want to do our equilibrium. We want to know what is the pH of a 0.25 molar H2CO3 solution. All right? I have my equilibrium equations written. Okay? So I'm going to do my standard ice table, where I have my initial concentration here is 0.25, 0, and 0. So what's my change going to be? Minus x, plus x, plus x. Okay? So I plug in over here. I'm going to do the exact same problem I've done. X squared over 0.25 minus x. We can see how small this is, so we know we can assume x is negligible. So my H plus is equal to the square root of 0.25 times 4.3 times 10 to the minus 7. So my H plus is equal to, somebody please.
3.28 times 10 to the minus 4. Good job.
What? 0.28?
3.
3.28 times 10 to the minus 4. Okay? So, that's what this concentration is going to be and what this concentration is going to be. Now, what's going to make this a little bit different is when we go to do our second hydrogen, now we're going to have to use these values over here. So our initial concentrations aren't necessarily going to be 0. So my initial concentration now of the bicarbonate is going to be my value of x, 3.28 times 10 to the minus 4th. My value of H plus is 3.28 times 10 to the minus 4th. That's my initial concentrations now. This is 0. Because we already have some H plus that got produced here. We have some of this that came from here. Okay? So now my change is going to be minus x, because we're always going to go towards 0. So it's going to be minus, you said y?
I said y.
We can do y.
Let's do y.
Plus y and plus y. Okay? So, we're going to do our exact same reaction now, is equal to 3.28 times 10 to the minus 4th plus y times y all over 3.28 times 10 to the minus 4th minus y. Now, we have 10 to the minus 4th as our initial concentrations, 10 to the minus 11th as the value of Ka. So what does that mean about the value of Y? It's going to be negligible, right? So if Y is negligible, what's going to happen to these two terms? They're going to cancel out. So Ka is going to equal Y. So in a polyprotic acid, the amount of H plus that's going to get produced is the only significant amount is going to come from the first hydrogen. The second hydrogen is going to be in very, very, very low concentrations, and so it's insignificant amounts. So reality is that for a polyprotic, for a diprotic acid, the carbonate ion is always going to be the Ka. That's going to be this concentration. The H plus is just going to be from the first, just doing like a normal monoprotic acid. You just go XX, or initial concentration minus X, and that's going to get you your H plus. To go through and do the second one, you don't even have to do it, because it's then going to end up canceling out to where the carbonate is going to be the same value as Ka2.
You need to show that step, like the whole 3.28.
I mean, it wouldn't hurt, but the reality is you can just say H plus is going to equal Ka2, which equals this value. So then,
Is that the CO3 2 minus?
the CO3 2 minus, that's what I meant. So, if we wanted to talk which substance is going to be in the greatest concentration as we go through here. So we have 0.25, we have the H plus, we have the HCO3 minus, and we have the CO3 2 minus. This is going to be the greatest concentration. What's the least concentrated? The CO3 2 minus. So if I put 0.25 molar of this into a solution, most of it's just going to stay as this. The reality is it's going to decompose into water and carbon dioxide, but if it didn't do that, it would be mostly this, least amount of this, and then between H plus and HCO3, which one are we going to have more of? H plus, because itty bitty little bit, a fraction amount of this is actually going to break apart and go to this. So, and that's going to make a fraction amount more of this. So there's going to be a fraction amount more H plus and a fraction less of the HCO3 minus. Right? Did y'all follow that?
Yes.
So that's one of the questions that they ask all the time, like a multiple choice. Which is going to be in the greatest abundance? Which one will be in the least abundance if you put this into water? Okay? So it's always going to be for a weak acid, this is going to be the most, and for a diprotic, this is always going to be the least. So if we had phosphoric acid,
We didn't find the actual pH.
what do we have to do?
Do we have to add 3.28
No.
and 5.6 something like that?
And what would you get if you added those two together? 3.28. So the pH is going to equal the negative log 3.28.
How did you know that?
No, it's going to be 0.25 minus 3.28.
Oh.
The
Oh,
H
no,
plus
sorry,
is going to be
yeah, sorry.
3.28 times 10 to the minus 4.
Sorry.
What was your question, Justin?
No.
I can know that by adding these two, because 10 to the minus 4th and 10 to the minus 11th, there's going to be 7 decimal places difference between when I'm adding and subtracting them. So to 2 or 3 sig figs. That's again why we can always make the assumption. Okay? I mean, it is going to change the value, but so little that we can negate it. We assume it's approximately equal to that.
How do you know if it's a polyprotic acid?
Because of this.
So like H2SO4.
Oh, okay.
H2SO4, H3PO4, H2C2O2, H2C2O4. Okay, so how many hydrogens?
What about strong acids like H2SO4?
Now, a strong acid H2SO4, you have to treat it 2 ways. You have to treat the first hydrogen as 100% ionized. Well, let's just do it.
Good.
What? It's that.
Oh, what do we get the pH final?
3.48.
3.48, just so we get that answer.
We're almost done.
H2SO4.
15 minutes.
I know, if you just wouldn't talk about it and worry about it so much, it would go faster.
It does worry me.
I know, but you focus on that, so a watch clock never boils. A watch clock never moves. Okay? So, H2SO4. goes to H plus SO4, H, SO4 minus. This is 100% strong acid. Okay? So if we start with a 0.25 molar, there is no Ka on this one because it's 100%. The Ka approaches infinity because this is approaching 0. But, so we have 0.25, well, we start with 0 and 0.
And you know it's 100% because it's a strong acid.
That's exactly right. So the change is minus 0.25 plus 0.25 plus 0.25. Okay? But now on our second one, HSO4 minus going to H plus SO4 2 minus. Now we have a Ka, and do they call it a 2? They call it a 1. It just we'll just say Ka is 1.2 times 10 to the minus 2. So now my initial concentration here is going to be 0.25. My H plus is going to be 0.25 and 0. This one is the only diprotic strong acid, so this is the only one you would do this problem on. Okay? So what's the change going to be here? Minus x. We're going to go plus x, plus x. Now here's another problem with this one. 0.25 minus x, x and x. So when I plug this into here, we get x squared, 0.25 minus x. Now we have 10 to the minus 1, 10 to the minus 2.
0.25 plus x.
Oh yeah, on the top.
So it does the same thing as the last one?
No, it doesn't. Why not?
There's not enough difference between the Ka and the
Because now we can't assume x is negligible.
Oh.
Because it's 10 to the minus 1 and 10 to the minus 2. So now we have to use fancy calculators.
You have to.
You have to. I mean, if you want to do the math
You
on
can have
that.
that on the test.
No, again, no.
Why can't you use it?
Because it's too small.
Because these two are too close to one another. So that means x isn't going to be insignificant compared to 0.25.
I don't have my graphic.
Okay? So somebody just do it.
Scott. Come on, Scott. You got it, boy?
They put this on the AP exam?
Nope. On the AP exam, you get to assume 100% ionization for both hydrogens.
Well, that's nice.
Huh? All right, so what do we get? X is equal to, really, just my SO4 2 minus concentration. It's taking a while to plug it in. Phew, I'm so glad I'm getting warm because I'm going to be freezing this afternoon.
Yes.
Any of y'all on lacrosse or soccer? No? Because Monday night they were out playing in the rain and it was...
If there are two possibilities for x, should we go with the...
Well, again, what are the two possibilities? What are the two answers?
0.27?
Okay, so can it be 0.27?
Yes.
Can you lose 0.27?
No.
So that's not a rational value. That's not a possible value because it's greater than what we started with.
0.011.
0.011?
Yes.
Okay? So that's my x. So therefore at equilibrium, this is 0.25 plus x. So it's going to equal 0.261. And this is going to equal 0.248, 249? 39, yeah. Okay? So that's going to be this concentration. That's this final H plus concentration is going to be here. So now the pH is the negative log of 0.261. Now notice it did again, the majority of the H plus came from the first one.
It's 0.58.
Is the pH.
5.58.
0.58. This is a strong acid.
Negative one. To the negative one.
Oh, yes, and negative 1.
I think you're wild and
Okay, so for this one strong acid, you would do 100%, but you still do the same procedure as what we're doing, where the H plus and the HSO4 carry over. Okay, but you have to treat this one as 100% ionized, then use the Ka, and you can't make the assumption, which is why they're never going to make you have to do it on the AP test, because they assume not everybody has the fancy calculators. All right. So let's look at H3PO4. Last one.
If you assume 100% ionization.
For both?
Yeah. So
Yeah.
it would be, H would be 0.5.
Yep. And if H is 0.5, what's the pH? What's the negative log of 0.5? Negative log of 0.5.
0.0, no, 0.3.
0.3. So the difference of 0.58 versus 0.3 if you assume 100%. Okay, because if you assume 100%, this would be 0.5.
That's not that much, is it?
Yeah. I mean, again, it's logarithmically it's significant, but for AP they let you assume either one.
Is various.
So you're not.
Damn.
You can't know.
Normal, simple electron, 101.
The other one is missing.
Okay. So now,
Where's my people?
here we go. Justin. Now we have H3PO4. Triprotic. So what are we going to do? 3 times. Okay? 3 times. So we're going to go H3.
Will you know the Ka for each one?
Yep. H3PO4 goes to H plus H2PO4 minus, which is the dihydrogen phosphate ion. So you go and you look up here on the table, and the Ka1 is 7.5 times 10 to the minus 3. Okay, then we go H2PO4 minus goes to H plus HPO4 2 minus, the monohydrogen phosphate. Ka2 is equal to 6.23 times 10 to the minus 8. And then Ka3, HPO4 2 minus, H plus, PO4 3 minus, Ka3.
It's 2.2 times 10 to the negative 13.
Maybe it's 4.8. That's what this packet says.
That's a what?
The packet says it's 4.8 times 10 to the negative 13.
This is, the
Well,
correct is 2.2.
2.2, it's not going to make a difference.
It's fine.
Did you write this packet?
Nope. It's different ways of calculating, I guess. I don't know.
It's fraudulent.
It's a fake video.
Okay, so if we start with 0.25 molar, 0 and 0, our change is going to be minus x plus x plus x. So we do this just like always, x squared. Now again, this one is going to be touch and go because it's 10 to the minus 3. So we really can't make the assumption on this one. So whoever's got the fancy calculator, go ahead and put that in.
Go Scott. Scott.
X is going to equal H plus.
I sold mine.
What?
I'm gonna buy it back
For more or less than what you sold it for.
Probably both.
Yeah.
Yes.
Okay, Scott, you putting this in? Yeah, I think you're the only one that's got that calculator out.
For money. You don't want to listen back.
Yes.
Alright. Like human tractor? I want my riding. Oh, that's right.
They color the paper. You really lost a lot of I do. Yeah, my yard is really. I do a push. It was really like 2.5
0.03.
0.03.
Like 397.
Yeah, it would take me like 6 hours.
Okay.
0.0397. So 0.04.
Okay.
So .040.
040. I'll do 397. Okay, so there's my initial. So now, this is 0.0397, 0.0397, 0, minus x, plus x, plus x. So now we're at 0.397, 0.0397, plus x times x all over 0.0397 minus x.
In that.
We can assume.
Now, we can assume that, right? So therefore this cancels out. So x is equal to my h, PO4, 2 minus, is equal to Ka, 6.23 times 10 to the minus 8. So now what do I do?
No, you add it.
So now again, that's now my initial here is going to be 6.23 times 10 to the minus 8. This is still 0.0397. This is 0. Okay, because we said 0.0397 plus x is still going to be approximately 0.0397.
You just plug it in and it's exactly that.
Yeah.
0.23.
Okay? So, our change now again is going to be minus x plus x plus x.
Oh.
So it's going to equal 0.0397 plus x, and 6.23 times 10 to the minus 8 minus x. Now again, what can we assume about x? Because we're at minus 8 minus 13, it's going to be negligible. So, but now these don't cancel out though.
But we can cancel.
Okay, the x's get rid of, but then you just go ahead and do it on your calculator, the simple math, just solving for x. This times this divided by that. Okay, you should be able to do that manipulation, knowing that the x's are canceling. Okay, so this is going to come up here, that's going to come to the bottom there. So what's x equal?
I got 3.45 times 10 to the power negative 19. So I can agree.
10 to the minus 19. That's a very small number. So in H3PO4, if you put some phosphoric acid into water, very, 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 very little of it is actually going to here. Okay? Which one is still going to be the majority? The H3PO4. That's the whole point of a weak acid. They don't ionize very much. And so then to go down each successive step, it's going to ionize even less. Therefore, this is going to be the greatest abundance. This is going to be the least abundant. This is the second most, well, H plus will be the second most abundant. Third most abundant. Fourth most abundant. Last most abundant. Okay?
The pH of that is 1.
So the pH is just going to be the negative log of the first one, which is equal to
1.40.
1.40.
I need a right meter.
Okay? So, to calculate the pH of polyprotic acids, the reality is that the pH is going to be as the result of the first hydrogen that gets donated. But to find the concentration of the other species, you just go whatever is your final concentration of the first one is the initial concentration of the second one. You just carry it through stepwise.
So if the question was, what is the pH of this, we just need to show the first step and then that's all.
Yeah.
Okay.
Because they're the same number. The assumption is that this number has to be at least 1,000 times bigger than this number, 10 to the 3. Okay? So since this is 10 to the minus 2, this is 10 to the minus 8, you got a difference of 6. You can assume that x is negative.
Yes, man.